All right, guys, welcome to section 4.8. We're going to be doing something called Newton's method. And Newton's method is very heavy on the calculator. So we're going to be using our calculator a lot in this section. So again, heavy calculator section. And in the syllabus, I said graphing calculators were helpful. Graphing calculators are helpful in this section. And I'll make a separate video to show you how they are helpful. Okay, so the ironic part is, so let me just kind of give a quick idea of what we're going to be doing. Essentially, we're going to take something that's irrational, so something like the square root of 6, and we're going to figure out an approximation for the square root of 6, up to however many decimals. And we're going to be able to do that approximation without using our calculator, right? And the ironic thing is that, we use our calculator to help with the calculations. So if we're using our calculator, why can't we just type in square root of 6? But it's nice to know how this method works. It's based in calculus. And a long time ago, when there were not calculators to tell us what the square root of 6 was, all the calculations we're going to be doing is just basic arithmetic. So we could at least have done the basic arithmetic by hand, even if it was slow and painful. But if we didn't have a calculator, we would be able to actually see what the square root of 6 was. So there you go. So let's talk about, the motivation. Well, we have one motivation, right? Square root of 6. If we didn't have a calculator, we wouldn't really know. We could guess, somewhere between 2 and 3, but that's it. But with Newton's method, we can get very accurate, up to 8 decimals, 10 decimals, 12 decimals, whatever level of accuracy we want. Okay, so to start, let's talk about the quadratic formula. And we could take any quadratic equation and we know how to solve it, whether there's rational zeros or irrational zeros. We know how to solve ax squared plus bx plus c equals 0, right? We use the quadratic formula. And we use the quadratic formula a couple times in our Math 190 class. It's very handy. And believe it or not, these types of formulas that help us solve degree 2 equations, they also exist for cubic equations and degree 4 equations. I'm not going to state the formulas. They're so complicated. Feel free to Google it because it's interesting. Complicated formulas are interesting. So formulas exist to find solutions for up to a degree 4 equation. So that means something like ax to the 4th plus bx cubed plus cx squared abcd dx plus e equals 0. There's a formula like the quadratic formula that would tell us the solutions for this equation. And then after that, it stops. So for a degree 5 equation, there's no formula. So no formula to solve degree 5 or higher equations. Okay, so for instance, something like 56 x to the 61st minus x to the 60th plus 1 equals 0, we don't really have a formula that would tell us what those zeros are. So how could we figure out the solution to this degree 61 equation? Well, one way we could do it is we could approximate the solutions using this Newton's method. And I'll explain what Newton's method is now. So we can at least approximate these solutions using Newton's method. Okay, so let's look at a graph. And let's say we were to graph this equation. You know, we're not actually going to graph it, but let's just say this is the graph of that equation, f. And if we wanted to solve the solution when it's equal to 0, that's like finding the roots of the equation. So I'm just going to write r. So if we want to find the solutions to that equation, f equals 0, the solution is r, because that's where our function f is 0. Okay? So here's what we're going to do. We're going to take a value x1, and you know, x1 can be calculated to us, x1 can be given to us, but essentially x1 is close to the root r. Okay, so x is close to the root r. And we've done that before. We've, you know, approximated roots. We've said they're between two values. That's the intermediate value theorem, stuff like that. So we would be able to find a number relatively close to the root. So that's what this R1 represents. It's a number relatively close to our root. And so what we're going to do is we're going to draw a tangent line, whoops, that's not very straight, at that point. All right, and hopefully yours is a little straighter. Mine didn't turn out very straight. And that tangent line we'll call L1. So x1 has a tangent line on f, and the tangent line is L1. So tangent line at x1 comma f of x1. Okay, and then this is what we're going to do. We're going to follow this tangent line, and we're going to consider the x-intercept right there. And we're going to call that x-intercept x2. All right, so again, x2 is the x-intercept of L1. Okay, and then notice that we started with x1, we created a tangent line and looked at that x-intercept. x2 is a better approximation of r. Okay, so, and here's why that works. We know, and we've talked about this before, if everything is close together, right, we have to do, you know, some sort of open interval around this r. If we look at the tangent line at x1, right, where x1 is close to r, we've talked about before how the tangent line can represent or is a great approximation of the function. Okay, so if we look at the x-intercept of that tangent line, that's going to be similar to the x-intercept of our function. Okay, so let me write that quick little note. Since L1 is very similar to the function, that means though the x-intercepts are going to be very similar. So in other words, we're getting a better estimate of r. x2 is closer to r. Okay, so let's write some things out. So L1, our original tangent line, hopefully we're well versed in how we write our tangent line. It's going to have slope f prime of x1 at the point x1 comma f of x1, okay? And so if we wanted to write the equation of L1, it would be y minus the y value is equal to the slope times x minus the x value. Okay, something like that. And then what we're going to do is we're going to look at the x-intercept. And the x-intercept is this x2. Okay, so let's consider the x-intercept, x2 comma 0, and this is going to give us an equation for x2. So I'm actually going to plug it in for the variables, right? Because, whoops, it's a point on that line. So y equals 0 and x is going to be x2. Okay, so minus f of x1 equal to f prime x1. And I actually wrote that in the wrong spot, so I'll fix it. It's an x value, it's the variable. Okay, so again, we substituted that x-intercept for x and y like we would do on the equation. So what I'm going to do is I'm going to solve this equation for x2. All right, and if you trace it, what would we have to do? We would have to distribute the slope, add anything that doesn't have x2 to the other side, and then divide out by the coefficient, and then we would get our equation for x2. And it's going to equal x1 minus f of x1 divided by f prime of x1. Okay, and again, this is our new estimate of r. So x2 is the new estimate of the root. Because remember what we're trying to do, and I'll remind you, I'll go up to the top, new estimate of r. What we're trying to do is we're trying to find equations to something complicated, right? So essentially we're trying to find roots to this big function, and that would be represented like that. This is where our function is 0. Okay, so we're just getting closer and closer to r. And then we're going to be able to repeat this process for however many degrees of accuracy we want. So let's try to just do round 2. Okay, we had r right here. We had our x1. You know, I'm going to do it farther away just so I can draw a pretty accurate picture. So let's have x1 be here. So let's say we just kind of zoomed in on everything. And then we had our tangent line, L1. And then this point right here, the x-intercept of the tangent line became L2. And what we're going to do is we're going to bring L2 up. Let me use, what color should I use? I need a green. Let's bring L2 up to the graph. Excuse me, x2. So right here. And now we're going to draw another tangent line. And we're going to call that tangent line L2. Okay, and now we have another x-intercept. And guess what? It's even closer to the root. All right, so you can see every time we repeat this process, we're going to go closer and closer and closer and closer. Okay, and then, you know, L2, we can have the equation. We're going to find it the same way we did before. All right, and then if we plug in this point right here, x30, just like we did before, we're going to get another estimate of x3. And it's obtained in the same way, so we should be seeing a pattern. All right, and we can repeat this again and again and again and again. And eventually, you know, we'll achieve a better and better accuracy. And then until finally, so we're going to get just closer, 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 closer to r. Maybe this little abstract point right here would be considered x of n plus 1, right? We can just keep going and going and going and going and going. And just looking at this, the pattern is we get x of n plus 1 from the previous x-intercept, so x of n. So this little formula right here is going to help us estimate that root. Okay, so that's a little formula that we should memorize. So I would say memorize this one. That will help you. All right, and then another way of doing what we're doing, let's say we looked at all of the x1s and the x2s and the x3s all the way up to the xn plus 1. We call that a sequence, going back to some pre-calculus vocabulary, and it's a sequence that will converge to r, the root of that function. All right, so again, that sequence is we start with x1, go to x2, x3, x4, you know, depending on how accurate we want to get, x to the nth, x to the n plus 1, and we can even go after, right? We can go on forever. And that would be us taking a limit of a sequence. And that limit is converging to r. Okay, so there you go. So that process of getting an initial estimate, finding the tangent, looking at that x-intercept, and repeating it over and over and over again to estimate r, that's Newton's method, okay? Before we look at an example, I want to show you some cases where sometimes Newton's method doesn't work. And you would know these situations because when we run Newton's method, we wouldn't get our xn's going to one number. Our xn's would be all over the place. So we would be able to see that they're not converging towards any number. So Newton's method won't always work. It won't always work for our choice, I should say, of that initial point, x1. So let me just kind of visually demonstrate this. So I'm going to draw something with a very quick change of rate of change. So maybe something that goes down very fast and then up like that. Okay, so we have this crazy function f, and a root would be right here. Right? So we would be wanting to estimate that r. And let's say we're going to estimate that r using, you know, an x1. And you can see x1 is relatively close to r. The problem with this is this function has a dramatic decrease of the rate of change, right? So at this point, our slope is, you know, kind of small. Our slope is small. And then if we were to draw that tangent line, it would get us all the way over here, right? And now we're very much farther away from your r. Okay, so it won't always work. But notice if we were to get our x1 a little bit closer to r, like maybe say we didn't choose that as x1, it was something a little bit closer, then that would remedy that situation. Okay, so Newton's method, again, won't always work for our choice of that initial x1. So it's just something to be aware of. Okay, but it can be remedied again by just scooting that x1 closer. Let's look at an example, and we're going to number 6 in the homework set. Number 6, use Newton's method with the specified initial approximation x1 to find x3, the third approximation to the root of the given equation. And we want to give our answer to 4 decimals. Okay, so we want to find the root of this equation. And our initial estimate is x1 equals -1. Okay, so that was nice that they gave us the initial estimate for the roots. Remember, let me just write a little side note here. If x1 isn't given, we could always determine x1. So we could always find x1 by using the IVT, right? And in this case, let's see, I'm just going to remind you, it's for continuous functions. We'd have to find one value on the function that was positive. F sub 0 is positive, for instance, and then f sub -1 is negative. It's negative 3, okay? So then by the IVT, there would be a root between -1 and 0. Okay, so I'm just going to do that as a thought bubble. That doesn't pertain to this problem. But if we ever had to use Newton's method and we didn't have a starting point, we could always find a starting point using the IVT. All right, so but onward, here we go. So it says use Newton's method. So let's write down that formula. And we need a lot of stuff, right? We need to find the function at x1. We need to find the derivative as well. Okay? So we have x1, so we're good to go on that. We want to find x2. So x2, just using our formula, so n plus 1 is 2. So n in this case is 1. And then 1 plus 1 is 2. So it's going to be x of 1 minus f of x sub 1 divided by f prime of x sub 1. Okay, so let's figure out everything that we need. So we're going to need what f of 1 is. And we're going to need, whoops, oh no, and we're going to need what f prime of x sub 1 is. So before I write that, let's do a little scratch work. That's a lot of stuff, right? It's a yellow. Okay, so f of x1 is f of -1, because it's given, right? So let's see. -1 cubed is -1, so it's going to be -2 minus 3. -1 squared is positive 1, so it'll be -3 plus 2. So it equals -3, okay? And then let's figure out the derivative of our function. So again, this is what we're calling our f. It's going to be 6x squared minus 6x plus 0. And then so f of x1, f derivative of x1. All right, again, -1 is just positive 1, so 6 minus a -6, 6 plus 6. Okay, so just plugging in all our things. All right, so then x2 is equal to x1, which is -1, minus f of x1. We determined that was -3, divided by 12. All right, so it's -1 minus becomes plus 3 over 12. So -1 plus a fourth is -3/4. All right, so that's your x2. Okay. So we're instructed to go one more round. They want us to find x3. So let's find that. And x3, according to our formula, will be x2 minus f of x2 divided by f prime of x2. Okay, and x2 is -3/4. That's what we just calculated. -3/4. Okay, so again, just for the interest of calculating, because we would be putting this in our calculator, 3/4 is the same as 0.75. So I would actually put this as -0.75 in my calculator. I think that would be much easier. All right, so again, this is our function f, 2x cubed minus 3x squared plus 2. Throw in a -0.05. negative 0.75. Don't round, no rounding allowed. We would get this. And then we have our f prime of x, 6x squared minus 6x. If we plug in a negative 0.75, we would get 7.875. And again, don't round. Okay, so since we're trying to estimate a root, we don't want to estimate in the middle of the estimation. Then we'll just get too far off. Okay? All right, so then x3, what's it equal? So you can write negative 0.75. You can write negative 3/4 for x2 minus, the top is that negative 0.53125 over 7.875. Okay, again, all of this we would be able to do. It's just basic arithmetic. It'd be tedious, but we could do it. Okay, this is not solvable using basic arithmetic. Okay, so, but we're going to use our calculator anyway, just to expedite that. And the instructions are, again, to find x3, and they want to give our answer in 4 decimals. So put that in your calculator, and we would get approximately negative 0.6825. All right, and then that is an estimation for a solution to this equation. And you can try that out too. If you take that x3 and you plug it into this function, you're going to see we get pretty close to 0. It's a pretty good estimation. All right, so that's Newton's method. What else can we do with this? Let's take a look at the following situation. So I started this by saying, what if we wanted to estimate the square root of 6? So let's talk about that issue, but let's make it more complicated. So suppose we want to approximate the 8th root of 500 to 8 decimals, I should say, to 8 decimals. How are we going to do that? Okay, so again, I think the key is right here is 8 decimals, right? We can definitely approximate the 8th root of 500. We can find perfect 8ths that 500 is between. I know 2 to the 8th and 3 to the 8th are, nestling or sandwiching that 500. 2 to the 8 is 256. And 3 to the 8th is 6,561. Okay, so, if we take the 8th root of everything, that would give us an approximation of the 8th root of 500. The 8th root of 500 is between 2 and 3. All right, so we're done. However, it's this next part that's important. We want to approximate it to 8 decimals. We just approximated it to the nearest integer. Okay, so how are we going to do this? Well, we're going to use Newton's method. So that means we're going to be using this formula. And then looking at this formula, notice we need a function. And the 8th root of 500 isn't a function. Okay, but remember what this function is. This function for Newton's method is set up by the equation, right? We're finding roots. Newton's method finds roots to this equation. Okay, so f of x should be solving, or should be the function we use here, where the root, or where the x is going to be the 8th root of 500. Okay, so if this is what we want to estimate, then this has to be a solution to the equation f of x equals 0. If that's what we're estimating, it has to be the solution to f of x equals 0. Okay, so I can write that into words. We need a function that has a root r, x, whatever, 8th root of 500. Okay, so we can go about it systematically, like what I had up there. We want to end up here. What's one way you would simplify it? Just kind of going with your gut. We can raise both sides to the 8th power. That will cancel the root sign. And then subtract 500. All right, so if we call this f of x, now the 8th root of 500 is a root of this, right? Because we engineered it backwards engineering. So that's the function we get to use, okay? So there you go. So now that we have our function, let's say that, f of x is this function we've just created, and we created it so this thing we want to estimate, the 8th root of 500, is the root. We are being strategic. We also need the derivative in Newton's method. Whoops, I was getting ahead of myself. 8x to the 7th. Okay, and now we're ready to use Newton's method. The only thing is, what else do we need in Newton's method? We need a starting point. We need x1. Okay, so we have our function. Now what we have to do next is find x1. And again, x1 is the first approximation of the root. Okay, and then we're going to do that by using the IVT, intermediate value theorem. Okay, so we have a continuous function. Polynomials are continuous. So we would have to, all right, so we're going to have to find two values to use the IVT, one that's negative and then one value that will make the function positive. So let me rewrite the function so everything is here. Okay, so, well, we kind of hinted at it before that we know the roots between 2 and 3, because 2 to the 8th minus 500, 2 to the 8 is less than 500, so that's going to be your negative root, and then 3 to the 8th is more than 500. So that's going to be your greater than 0, okay? So, oops. That means by the IVT, the root is going to be between f of 2 and f of 3, okay? And again, that means that that 8th root of 500 is between 2 and 3, okay? That's what we discovered last time. All right, so by the IVT, a root is between 2 and 3. All right, and we can choose either number, but because we know a lot of these numbers, excuse me, where am I going? all the way up here, right? 500 is much closer to 256 than 500 is to 6,561. So I'm going to choose our starting point to be 2. So that's L1. Excuse me, that's X1. So I'm going to choose X1 to be 2, since it's closer to the 8th root of 500. Okay. So we want to estimate this 8th root of 500. How many decimal places? To 8 decimals, okay? So that means we're going to have to keep doing Newton's method until our estimate is 8 decimals accurate, okay? So it means we're not going to see any changes in the first 8 decimals. That's how we know we're getting that kind of accuracy, okay? And when we're showing our work on the exam, I'm going to want you guys to write out all of, your X1, your X2, X3, X4, X5, X6, et cetera, et cetera. All right, so we would say, this is the kind of work we would show. We would say X1 is equal to 2, all right? And then X2 is going to be, X1 minus f of X1 over f prime of X1. Or alternatively, since we know X1 is 2, we can also write it as 2. Okay, and then off to the side, like we know what F2 is, so lots of scratch work. And again, in the next video, I'll show you how we can quickly do it on our calculator. We could calculate F2, so 2 to the 8 minus 500. And then f prime of 2 would be 8 times 2 to the 7th, okay? And we'd plug it into the numerator, plug it into the denominator. And then we'd have to put it all in our calculator. And remember, don't round, but the work you would do on your paper, just give me what your calculator spits out and tell me all decimal places. And that's what your calculator should give you, okay? And then we go again. We'd have to do X3. Okay, and we'd have similar side work for now, right? I'll show you again the shortcut. In the next video. Okay, but you're seeing how tedious these which is why I said it's a big calculator section. Okay, so all right, and you would get your numbers, and then whatever you get, you would plug into the numerator and the denominator. Okay, so these just big calculations, and you would get this. Okay, and then try the pattern. These numbers are ginormous. And again, right now, if you have your scientific calculator, you would just have to plug in all of these numbers individually, right? I can do it like this. So this is what your entry could look like on your calculator. So here's X2. Let me make sure I write it down right. Okay, minus, then you need parentheses around X2 to the 8th minus 500. Then you'd hit the divide sign, parentheses, 8 times, parentheses are important or else we don't do order of operations, 8, 1, 2, 5 to the 7th. Okay, and then when you push enter, that's how you get that 2.180559717, okay? And you would repeat this whole process, all right, with the next number. So for instance, for x4, here's what x3 was. All right, that's your x3. And then you would take x3, you would plug it in to your function. All right, parentheses, so we don't just divide the last term. And then we have our derivative, 8 times x3 to the 7th. Okay, and then if we do that for x4, we get this. All right, and now at this point, notice our ones decimal. Wait, let me make sure I write this down right. x4 is 0.174616,751. All right, and I'm going to compare it to x3. All right, so right now it looks like the 2 and the 1 are stable, but we want 8 decimal places to be stable, so we got to keep going. And you're going to repeat that process, and let me just show you what you get for the next ones, because it's the same thing, you're just plugging in a new number. So here's x5, 2.174559,281. Okay, and now it looks like the 2.17 is stable. X to the 6, 2.174559,276. So now that's all stable. See how it's the same from above? 1745592, and then it changes. So what is that? 1, 2, 3, 4, 5, 6, 7, almost done, because we need 8 decimal places to be stable. And notice x to the 7th is 2.174559,276. All right, and then the whole thing, 1, 2, 3, 4, 5, 6, 7, 8, 9. So in this case, we're actually going out a little farther. So that is telling us then, so remember that was an estimate of the root of that function x to the 8th minus 500. So we're saying it's approximately x to the 7th, 2.17455927. 1, 2, 3, 4, 5, 6, 7, 8. I'm just going to write the 6 there too. So there you go. So that would be your solution. And then as far as showing work, it's so calculator dependent. I mean, what I have is fine, right? You show the initial formula. You might show how you plug in one. And then you can just, after that point, list, x2, x3, x4, x5, x6, all the way down to x to the 7th. All right, so that's how you would do it on a scientific calculator. In the next video, we're going to do a new problem, and I'm going to show you how to find the solution on a graphing calculator. Okay, and the graphing calculator, it's a little bit more efficient, but if you don't have a graphing calculator, that's fine. You can use your scientific calculator, and please still watch the video because we're going to be solving a new problem. We're going to be finding, again, the positive roots correct to 6 decimals. Whoops. Decimals. And the equation is 3 sine x equals x. All right, so we're going to examine that in our next video in part 2.
I can learn to understand you much better.
Thank you.